So last week we have started and finished the microcanonical ensemble. Right, we're already over it. So for microcanonical ensemble, if you remember, all the states are equally probable. For a given energy. Okay. Now, the way to solve or to approach any problem where we assume a microcanonical ensemble is to say the following. We have to count the number of states for a given energy. Okay. Afterwards, we connect omega, the number of states, to the entropy of the system by stating that the entropy is K Boltzmann of log of omega. Okay. And then we have the following connection to the thermodynamical equation by saying that 1 over T is ds EdE. Most of the problems that are related to microcanonical ensemble are hard to solve, technically hard to solve. Why? This step over here of saying how many states do I have for a given energy. So if the system is simple enough, like the two-state model that we solved on Tuesday, yeah, it can be done. The moment I introduce additional constraints or additional degrees of freedom, it becomes more and more complicated. Actually, rises up exponentially fast, the difficulty of the problems. And afterwards, we have to take huge number of different derivatives using the Stirling approximation usually. So it can be done, okay, for this simple approximation of canonical ensemble, but it's difficult, technically difficult, and we're not completely sure about this initial assumption. All the states are equally probable. So what we are going to do next is to introduce something that, in some sense, looks like more advanced and more difficult setting, which we call canonical ensemble. But it's actually going to be much more easier to solve any given physical problem assuming canonical ensemble and not microcanonical ensemble. All right, so if you remember, this point over here is basically, we assume some sort of a uniform distribution of all the states, right? So the only thing that we needed to count is the number of states, and the moment that we know the number of states, the probability to be in a given state is just 1 over the number of states. Okay, so this is, over here, is uniform distribution. Okay, so back to probability 101. After we study uniform distribution, what we study next? No. Something which is even distribution. No. Conditional uniform distribution.
We did it in the math department, not in the physics.
So you don't know probability at all. or you know a lot about probability, not actually what to do.
More about
I'm filmed. All right. So what it actually is. So if you remember the set of all states, omega, and if conditional distribution or conditional probability says the following. Let's assume that we have B as our state, and we condition that B actually occurs. Okay. Then we want to compute. We want to compute what? The probability of A given B. Okay? So this is the conditional probability. We know that B have occurred, okay, and we want to compute the probability of A given B. Now, if everything is uniform, this probability is simply the number of states or the number of outcomes of our experiment that belong to A divided not by the total number of experiments that or outcomes that we have in an experiment, but actually divided by the total number of outcomes in B. So this is the expression, very simple expression, yes, for conditional probability with uniform setting. Yes?
You assume that A is the whole A.
Great. So basically, you're right. So this is when A is inside. But if I'm looking on some other setting where A is only partially inside, for example, this guy. So this is A cat with B. Intersection. Yes. Great. Now, the moment that we know this, we can continue the same prescription as we used before. Right? So we know, great, we have now some sort of probability. We are going to use the number of states for B, the number of states for A, okay? And we're going to connect the number of states to entropies by the same law that we already used for microcanonical ensemble. Okay? So this is the connection. It's not just, let's assume uniform distributions, but we need to connect it to some physical quantities. Number of states always connected somehow to entropy, right? So we are going to use the microcanonical setting for those numbers, the number of states at A intersection B and the number of states at B. All right, so how we do it? So what is our system? In general, we assume now the following setting. So this is the total system. This is our reservoir. Okay. Heat bath. If we have, and inside this heat bath, we have our system. Now, this system can have different energies. So EI, energetic state, number I of the system. Now, for microcanonical ensemble, we always assume what? That the energy is always constant. Here we assume that there can be some sort of a exchange between the system and the general reservoir of energies. Okay, so the energy of our system can be modified. What cannot be modified? The total energy of the system and the reservoir. Okay, so total energy of the system plus reservoir of the heat bath is constant. Okay. Now, it looks like something which is a little bit more complicated, right? So you now don't have something which is very constant, like the energy of the microcanonical ensemble. There's some sort of exchange that can be performed between the heat bath and the system. So we can think, wow, that's going to be a little bit, not a little bit, but much more complicated than this microcanonical ensemble, but actually the other way around. Okay? We lose something is the constant energy, but we gain something, this flexibility of calculating many physical quantities. Let's see how it's done. Okay, so constraints I can have, or the system that we are interested in, can attain many different energies. The total energy is constant, so we know that E total it equals to E reservoir plus E system. A system can attain different values. E reservoir can attain different values. E total stays the same. And there is an additional constraint that the temperature of our heat bath, of our reservoir, is always kept constant. Okay. So there is an exchange of energy, we can say an exchange of heat between the system and the reservoir, but this exchange happens such that the energy, the temperature of the system is not modified.
The reservoir.
Yeah.
Not the system.
And the system, what is the temperature of the system? We assume that there is an equilibrium between the system and the reservoir at all times. So if the temperature of the reservoir is T, the temperature of the system is also T. Okay? We assume equilibrium and we treat everything that we are doing for microcanonical ensemble, for canonical ensemble, we always assume equilibrium between something and something. So here, it's a closed system, it's an equilibrium, and there is also an equilibrium between the system and the T constant. So if you want to say that all the other intensity quantities are equal between the system and the reservoir, you are completely right. Alright, so now that we know all of those assumptions, we can go back to this definition of conditional probability that we use for canonical ensemble and try to compute the probability of a system to be in a specific state with energy EI. So f of I, the probability of the system to be in a state with the system equals to EI. So what that equals, according to this formula over here, is the number of states, okay, number of states of what? Of the reservoir E total minus EI divided by the number of states, okay, of what? Of the whole system, reservoir, and the system, of E total. Alright? So, conditional probability, you're looking at the number of system or on the number of states that are related to the reservoir, you're looking on the total constrained number of states, which is what? For the system. On the reservoir, we use this ratio over here, and this is our probability. The next step is to say, alright, how this guy related to entropy and how that guy related to entropy. So instead of denominator and numerator where we have number of states, we're going to submit something which is related to entropies. Alright. So how it goes. So S total equals to K Boltzmann multiplied by log of omega total of E total. Okay, what else? We have S of reservoir equals to K Boltzmann log of what? Log of omega of reservoir. E total minus EI. So now I'm going to use, instead of omega total on omega reservoir, I'm going to submit the quantities that relate on the entropies of the total system and the entropy of the reservoir. Okay, so from this guy, what I'm getting that 1 over K Boltzmann S total to the power of E equals to omega total of E total. This guy gives me that E to the power of 1 over K Boltzmann S of reservoir equals to omega reservoir of what? Of E total minus EI. Right. we push both of those into this expression, and we're getting that Fi equals to e to the power 1 over k Boltzmann S reservoir divided by e to the power 1 over k Boltzmann S total. Now, this is not exactly enough. Why? So first of all, I can say this is S total of what? Of E total. And there, here S reservoir of what? Of E total minus EI. Nice. Now, the next step is somehow to relate the entropy of the reservoir and the entropy of the total system, this and that. Okay, so first of all, I can say the following. So S total, because we're assuming extensivity over here, it is the entropy over the reservoir plus the entropy of the system. Okay. So I can say that S total, E total, is the sum of the entropy of the system plus the entropy of the reservoir. Now I can make also another trick. What is my additional trick? I can say, but at what energy I'm computing the entropy of the system. The entropy of the system can be modified. It can be E1, E2, E3, E4, E5, E7. So what I'm going to push inside here? I'm saying, well, let's push some general entropy. Some general energy. What exactly is energy? I don't know. Let's put something. Let's call it U. Okay. We'll later see what this U is actually is. For now, we're just putting some sort of an energy that the system can have. Okay. What is S of reservoir? E total minus U. Okay. So nothing bad happens over here. This is extensivity. And we always assume that our systems are large and big and extensive, so entropy is an extensive quantity, so everything is good over here. Alright, so this will go somehow inside. So we see already that in the denominator we have S of reservoir and S of system. Now here in the numerator we still only have S of reservoir, and I want to develop it a little bit more. I don't want to use just S of reservoir of E total minus EI. I want to introduce another quantity. What this additional quantity is going to be? Temperature. Somehow temperature have to go inside of this formula. Right now we have entropies. Okay, we have energies. Remember, we don't like entropy. Why? Because we cannot really do something with it. For now it is. So we want to introduce temperature. Okay. How we're going to do it? So we're going to take this guy, S reservoir, of E total minus EI. And first of all, we do some sort of a connection to what we already have in the denominator. So we have here S system of U plus S reservoir E total minus U. So here I'm going to have S reservoir of E total minus U. Okay, so over here I also want to have something which is related to E total minus U. I remind you, I don't really know what U is yet, but we'll know it soon enough. Okay, so how to relate this guy to that guy? So first of all, we'll do something like S reservoir is E total minus U plus U minus EI. Okay. So I just added and subtracted U inside those parentheses. Next is to say, great, so I have E total minus U over here. I have E total minus U over here. Now I can assume that maybe U minus EI is not that big.
Why? Why like that?
Why not? Why not? So what was written over here? That T equals constant. And I'm going to use this assumption in a second, and you will understand why write it in this following form. Just 1 second.
Because the temperature is the derivative of the...
Exactly. I'm going to Taylor expand this guy. I'm going to Taylor expand this with respect to what? To the energy around which quantity? E total minus U. Okay? So I'm expanding as reservoir of E total minus U plus U minus EI equals to approximately. I don't know what this sign means, but approximately equals to as reservoir of E total minus U. So you agree with me when U minus EI equals 0, this is exactly right. Okay. Next term I need to provide to you the derivative, right? Plus dou S reservoir dou E, right? At E total minus U multiplied by U minus EI. Alright, so this is nice. Why it's nice? Because, as you said, what is this guy?
1 over 10.
1 over T. So this is 1 over T. Okay, but you can say, and this was your question maybe, why to stop over there? Why it's small? Maybe it's large. Maybe it's tremendous. And the answer is, I don't care. Why do I don't care? Because T is constant. Okay, so what is going to be the second derivative? D squared S to dE squared. It is D to dE of 1 over T. T is constant. This is 0. And the next derivative and the next derivative, all the other derivatives, due to my assumption, physical assumption, that the temperature is not changing, everything else simply does not exist. Okay? So this is why I use this U minus UI and expanding Taylor series, because I have a physical assumption about this quantity. Okay? You can say, Stas, well, maybe it's not a real physical system that the temperature is constant. Yeah, but there is also not a real microcanonical ensemble, and this is some sort of approximation. But it's a very useful approximation. Great. So let's see what we got so far. So S reservoir, or we can start from this guy, S reservoir of E total minus EI equals to S reservoir of E total minus U plus 1 over T U minus EI. Okay. So this is this guy. Okay. And this is this guy. Okay. So the only thing left is just to, instead of writing this reservoir in S total, use those equations. Right? U is, so what is the difference between U and EI? EI are some energetic levels of the system. U is a quantity that I put inside. I'm so far don't know what it is.
Quantity of what?
It's an energy of the system.
EI is then.
And U is some sort of an energy. I don't know what it is yet. Okay? So you can ask me, I can ask you the following question. Have I performed something not correct mathematically? I haven't defined U, right? But I said there is an energy U that I'm going to use. I won't tell you so far what it is, but there is an energy of the system. Can I do all of those tricks? Yeah. So that's enough for me for now, but I have a depth. I have to explain to you explicitly what this U is. Don't worry, we'll solve everything by the end of this class. Okay. So, a little bit of algebra. Let's see. So we have e to the power 1 over k Boltzmann. What we have inside? S reservoir e total minus ei, this guy. So it is S reservoir of e total. Yeah. And I'm fine. S reservoir of what we have, e total minus u plus 1 over t u minus ei. Okay. And over here I have e to the power 1 over k Boltzmann. And here I have S total of e total, which is S system of u plus S reservoir of e total minus u. Okay. So let's put everything in one long line. So we have e over 1k Boltzmann, S reservoir of e total minus u plus 1 over t u minus ei minus S system of u minus S reservoir of e total minus u. Okay, some of those things are erased immediately. Okay, and we are left with something very nice. We have here e to the 1 over k Boltzmann over t, and then I introduce t inside, so we have u minus ei minus S system minus t S system of u. Now, this is already an achievement. Why it's an achievement? Look on the variables. If when I started with what? I started the total number of states for the whole system plus my system and the reservoir. Now, I don't care about the reservoir anymore. I have temperature, which is constant. I have the entropy of the system, which is very nice. I have some energy which is related to the system. I don't know what it is yet, but I will know. And I have ei, which are energies of my system. Okay. We can even write it a little bit more nicer. We can write over here e over beta, where I say 1k Boltzmann t equals to beta, of what? Of u minus ts system over u multiplied by e to minus ei beta. And this is fi. This is a very important formula. So first of all, what is this? This is the free energy. This is the Helmholtz free energy. This is F. Free energy. Now, this guy I can actually now relate to, this is a physical quantity. Right? So remember what we have done in microcanonical ensemble. In microcanonical ensemble, we computed the entropy, and then we used that the derivative of the entropy with respect to energy is 1 over the temperature. Here, we are getting an expression of the free energy, okay, u minus t, S of system, of the free energy of what? Of our system, and it's somehow related to the probabilities of occupying different states. Okay. Why it's wonderful? Because if this is a probability, I know something about all the probabilities. What do I know about the probabilities? What I know about all the probabilities together, taken together. It has to be equals to 1. So sigma of I of fi equals to 1. Right? Because it's probability, the probability has to be normalized, And this is the normalization, so they always have to be satisfied. Yes?
Is it also true when you did this? That is not exactly right. So when you're doing those stuff, you need to be careful.
I always careful. And you're right. I need, so what I actually need, that the temperature is not changing. My temperature is constant. Okay? This is a strong assumption, physical strong assumption. So whatever is happening, the temperature is constant. Okay, so let's see if we can use this constraint in order to get a feeling, get a formula, get something about this is physical thermodynamical quantity. I can use Maxwell, whatever you don't like from thermodynamics. Okay, so all of the stuff that you don't like about thermodynamics, you can use it in order to compute whatever you like by looking on the free energy. Because the moment that you have free energy, you can compute everything. Remember, this is why we studied thermodynamics. All the macroscopical quantities, pressure, conductivity, whatever, it's always inside the free energy. So the moment I know how to describe free energy by some microscopical states, okay, or microscopical quantities, it's a great achievement. Okay, so we have a sum over I e to the power beta of F system. Let's use U minus TS. It's easier. Multiply e to the power minus beta EI equals 1. So I have e to the power beta U minus TS multiplied by sum over from I of e to the power minus beta EI equals 1. This is not related to U, to the entropy of the system, to the temperature. Well, it's related to the temperature because there is temperature inside beta, right? But it's not related to whatever I'm thinking U is and S is. Okay? So I'm just going to say that this sum, it is Z, and it has a specific name, and it is probably the most important function or quantity in equilibrium statistical mechanics. This is the partition function. Funkcja chaluka in Hebrew. This I know. And what we have that e to the power beta of F, the free energy, multiplied by Z equals to 1. Okay. This means that e to the power beta of F equals 1 over Z. Okay. This means that F equals to 1 over beta minus log of Z. So the moment I know what's the temperature of the system, and I have to know it because this was my original assumption that there is a constant temperature of the heat bath reservoir, my system, all right? The moment that I know all the different energies of my system, this is not macroscopical description, this is a microscopical description. I can compute the partition function, and the moment that I know partition function, I can compute this free energy F. You can say, Stas, this is great, but in this S, it's this function U, and you still haven't told us what this U is, so it's a little bit useless, but we're getting there. Okay? So if I know U, I know to compute the free energy, and I know all the different thermodynamical quantities and how they are related to the microscopical description of the system. So this is the bridge between this guy over here, between the macroscopical description by using thermodynamics and microscopical description by using the energies and the states of the system. And you see it's very important what kind of states do I have, what kind of energies do I have.
What happens if I have a continuous dependence on E?
Alright, we'll get there. We'll get there. It's a little bit different, but all what changes is that we're going to have, instead of a sum, an integral, and there should be some sort of a density of states. We're getting there. It's very similar to what you have learned in the regular mechanics of how you compute mass. If you have discrete masses, it's just a sum. And if you have a continuum mass, it's an integral of some density of the mass. Right? Okay. Now, it's actually very nice because we now can compute anything that we like, because look how I can describe now Fi. So Fi, instead of writing this e to the power beta f, okay, that stands over here, I can simply say this is 1 over z e to the power minus beta ei. Right? I actually don't need f there. I don't need u. I don't need anything. The probabilities are independent due to the normalization constraint. They're actually independent of this value u. Right? There is no u in z because z is a sum over I e to the power minus beta ei. You don't need u. It's not that I'm not going to tell you what u is, but you don't actually need it for the probabilities. And the moment you have probabilities, you can compute whatever you like. So for example, what is the average energy of my system? Right? There is no constant energy because my system can actually, the energy of my system is not constant. Right? Because I have interactions with the reservoir, we are exchanging heat with whatever we exchange, and the energy of my system is bouncing up and down through different states, all the different states that are described by Ei. So I don't have a specific energy, but I can speak now about a specific average energy. So this is what we lose when we switch from microcanonical ensemble to canonical ensemble. In microcanonical ensemble, there was an energy. All the states were exactly the same probability-wise, and there was a very specific energy to the system that wasn't modified as a function of time. For canonical description, this is already not true. So we losing the constraint of constant energy for what? In order to get a tool, in order to get something at our hands that we can use and compute. So of just computing the number of states, we don't need to compute any number of states to compute probabilities now. We don't care about the number of states. Oh, maybe a little bit when you compute the sum, but it's not that you need to compute all different combinatorial functions or expressions. But you don't have a constant energy, you have an average energy, which is actually fine because most of the physical systems that we look on, there is no constant energy. There is always some small fluctuations as a function of time. How we compute it? Probability 101. What is this?
Sum over Ei, the probability.
Ei Fi. Right? This is the definition of for the average energy. Great. Sum over I, Ei, what we have over here, 1 over z, e to the power minus beta Ei. Do we have a nicer expression? Can we have a nicer expression? So of course we do. Okay, we can take 1 over z out, and inside we have sum over I, Ei, e to the power minus beta Ei. What do we do next? Derivative, right. So it's like a Feynman trick for discrete sums. Do you know what Feynman trick is?
Yes. Switching the integral.
Haven't you seen the Big Bang Theory? The trick is there in two episodes at least. So the Feynman trick is to, if you have an integral, instead of performing the integral, you see that you can describe the integrand as some sort of a derivative. So we have a summation over here. So instead of performing the sum, I say, well, this over here is, let's describe it as a derivative of what? Of something with respect not to I, but with respect to something else, which is beta. So I'm saying that this is 1 over z, a sum, and here I have minus d to the beta of e to the power minus beta ei. Right? So if I'm taking the derivative with respect to beta of this guy, ei goes downwards, minus goes downwards, and I'm getting this expression. This is the Feynman trick for series. Next step, what do? We're physicists, so we're always allowed to do this. We take d to the d beta outside of the summation.
It's true because it's a positive.
Don't argue. It's for physicists. It's always allowed until it's not allowed, but it's always allowed. Minus d to d beta, a sum over I, e to the minus beta I. The Hebrew definition is מתכנס במידה שווה. I don't know what's the translation to English of why I can do it, but I can do it.
Uniform.
Whatever, I don't know. Okay. Now, what is this? This is why we're doing this. What? What is this? Z. So we have 1 over z, d to d beta, and we have minus of z, which is minus d beta of log of z. Yep. Okay, so we have that average E equals to minus d to d beta of log of z. Well, yeah, this is nice. Z depends only on the what? On the energies and the number of energies that I have inside. Very nice expression. But I can actually use this expression to tell you something about what? About U. Remember this U? Appears over here, appears over there. There is a U inside. I haven't told you what this U is, but since there is a connection between log of z and f, and between f and u minus ts, right? I'm going to use this expression over here to actually define what u have I used. All right. So d to the beta, 1 over beta. Yes, question.
If you say that the temperature is constant and beta is 1 over
K Boltzmann T.
T, so beta is also a constant.
Beta is constant.
So how could you derive with something which is constant?
It's a parameter. Why not?
That is constant.
In finance, it's also different.
So what? It's my parameter over here. Can I use it schematically?
Okay, yeah, sure.
Again, the answer is, have I done something wrong mathematically?
Okay.
I haven't. Okay, so all of this is just expressions. You don't like the d to the beta of log of z, don't do it. Use this. Compute it by hand each time. This is a trick, mathematical trick of how to write this formula in much nicer form. That's all. But this is true every time that you have a function and you have some parameters inside a function. You can take a derivative with respect to those parameters. Although they are constant, but you can still take a derivative and then say t equals to something. Alright, so I have d to d beta. What is log of z? Minus beta f. Minus beta f. Okay, so what it is? F plus
The derivative of f with respect to beta.
df to d beta
Times beta.
times beta. Okay, what's the next step? So it is f plus beta df to dt dt to d beta. Okay. So this is f plus beta. What else? Do I have minus somewhere? I have minus.
No, it's
Okay.
okay.
It's fine. So what is t? Remember, so 1 over k Boltzmann t is beta. Okay, so t equals to 1 over k Boltzmann beta. So here I have plus beta df to dt, and instead of dt to d beta, I write d to the beta of 1 over beta k Boltzmann.
Can you, the reference to the t isn't it just the entropy?
Negative.
A negative entropy?
We'll get there. We'll get there, yes. yes.
Avoid
We're getting to this function somehow. Okay. So this is F plus beta dou F to dou T, and this derivative is what? Is minus 1 over beta squared K Boltzmann. Okay. What? Yep. You'll see in a second. So we have minus beta divided by beta squared by K Boltzmann dF to dt. It is what? F. So what we have? Beta divided by beta squared is 1 over beta, K Boltzmann, as a temperature. Minus T dF to dt. Now remember, dF equals minus S dt minus P dV. Okay? Which means that dF to dt is minus S equals to F plus Ts, which is U. Okay? Which is U. So what we got is that the average energy equals to U. We haven't taken some energy and expanded around some energy. We have taken the average energy of the system. Okay? This is what we have done. Alright, so remember this connection that we have, which is F equals minus 1 over beta log of Z. It's computed for what? For the average energy. And the free energy is the average free energy. So all the thermodynamical laws, and I think I mentioned it, but this is actually the proof, all the thermodynamical laws that we have used are not for constant energy, not for constant free energy, not for constant enthalpy, even not for constant entropy. They are for average energies, average free energies. Our potentials, thermodynamical potentials, are average potentials. Because if we actually look on the system, on a real system, and this is the energy as a function of time, it's never constant. Okay? So if we try and perform some measurement in a lab, we will see fluctuations. It's just something that dances around a constant value. This constant value, this is U. So everything that we have learned in thermodynamics, it's about averages, how the averages behave. This is why everything was continuous. No fluctuations, there is always a specific value, because on average, this is what we do on the system. We heat it up, on average the energy grows. We cool it down, on average the energy decreases. On average, there are always fluctuations. Where are we getting those fluctuations from, or the descriptions of those fluctuations? Microscopical description. We need to understand that there are actual energetic levels, that the system can have different energies, that there are always fluctuations that taking the system from one energy to another. On average, there is a constant energy. And thermodynamics relations describe those, those averages. But the true behavior is by probabilities that actually define those guys. Yes?
The way say that the total entropy equals to the entropy of the site in energy U. The energy of the other side.
Okay.
Energy total minus the U.
Yeah.
We know that in equilibrium, when we constrain the total energy,
Yes.
the entropy is maximal.
The entropy.
Minimal. Sorry.
Okay. Yes.
So now can we say that the inner division of the energy in equilibrium is the average?
So energy, or the entropy that we have defined, and the maximal value is the average energy in equilibrium. Yes. That's what can you say now. Right? Because if you define the energy by means of U, entropy by means of U, then the entropy that you have is also some sort of an average quantity. there is a microscopical description of energy, of entropy, right? For example, the log of states, and we will learn something that is called, but you know, Shannon entropy. Okay, so this is a microscopical description. Then it can have different values. The description that we have learned so far, that's coming from thermodynamics, is the average description. Okay. Yes.
We first assume that U is one of the energy states for
No.
the system.
We assume that it's some sort of an energy of the system.
Some sort of
energy
energy of the system.
Yeah, of the system, not of the reservoir.
Yeah, for example, if you think about a harmonic oscillator, you have a discrete amount of valid energy states.
Yes. So
The average
something.
of them not
I
have
picked
to
some-
be one of the energy.
So what? It's a big
energies of
system.
the
It's a big system. I can answer that. It's a big system, right? And I can pick some level. You can say, well, Stas, there are some modifications because maybe you haven't chose the right level. Maybe you chose something which is close enough. It doesn't really matter because the system, there is an assumption
Can be not
about.
close even.
It's an assumption of macroscopical description. So I'm assuming, and this is part of this assumption, is that the states are so close that it doesn't matter what U I chose. That's what was my assumption. It doesn't really matter what U I chose. Okay, there is always some specific state that is close to it. And moreover, second answer is that I couldn't care less because I defined the entropy with respect to some energy. Can the system have this energy or not? It's a different matter. Right? Yeah.
You at first chose the energy U sort of arbitrarily.
Not arbitrarily. I knew what I'm doing.
No, you.
I knew
said-
that. I knew it's not a miracle that I
said
obtained.
it
We
was-
started this. I knew that I started with this.
You said it was some energy. Now you got that starting with some energy had to be the average one.
Yes,
And
because
you're confused.
eventually
The calculations were
no. Because it's a very important quantity. Because eventually I've got that everything is described by this f. And it has to be the representative behavior. And what is the representative behavior? The average behavior. That's all. Any other questions? Yes?
This is the huge importance about stability, right? Because we have fluctuations and if we were in the stable.
Yep. So remember I've described what the stability relations are. So the stability relations they are saying you have fluctuations, but the fluctuations are such that the system always coming back to the equilibrium, and this defines all the the derivatives of the intensive variables with respect to extensive variables. Yes. Yeah.
But here you assume that the temperature is constant.
Yep.
But
For a given temperature, I compute anything. Then you give me another constant temperature, I can compute anything. Then you give me another constant temperature, I compute anything.
But the temperature is changing.
No. Physical setting. I have a reservoir, heat bath. I put inside my system. I let everything equilibrate. I set the temperature, and then I measure everything without changing the temperature. Okay, now I want to do an experiment with different energy, different temperature. I start all over again. I prepare my system from scratch. I set another temperature and do the measurement again. Okay? So the temperature is constant, and for temperature I can compute whatever I like. But it doesn't mean I cannot change it. I can change it and compute every other quantity by using the expressions that I have on board. Any other questions? Okie dokie. Okay, so now we have a prescription of what we actually do when we have canonical ensemble. For canonical ensemble, okay, 1. Obtain different energies of the system to compute z, which is sum over I of e to the power minus beta ei. If you're capable of doing those two tasks, you're done. Okay? The problem is it's difficult to obtain the energies, and it's difficult to compute this guy. Okay. All the examples that we are going to solve in this class are based on two very important settings, assumptions, conditions. Okay? We need to represent the energy in additive fashion. I will explain in a second what it means. Deal with uncorrelated degrees of freedom. So let me solve one simple example, and then I will explain exactly what I mean by the additive fashion and the uncorrelated degrees of freedom. So the first example that we're going to solve, this is the example that we solved on Tuesday, and it took something like 40 minutes. We're going to solve the example of two-state model. So what is a two-state model? We have n particles. Okay. We have a temperature. And we assume that each particle it's either 0 or epsilon. This is what we are going to assume. And we want to describe this, for example, we want to compute the free energy of the system. Because the moment that we know the free energy, we can compute specific heat, we can compute pressure, we can compute whatever we like. There are tons of Maxwell expressions and all the other expressions that you've been taught during thermodynamics. The moment that we know what is free energy, we are done. Okay? Then we need to derive something with respect to something. It's very easy. All right, so how we deal with this? We need to compute z, which is a sum over I, okay, e to the power minus beta ei, where ei's are all the different states that we have inside our system, or all the different energies. Now you can say to me, Stas, it's very difficult to compute all those different energies. Why? Because when none of the particles is excited, we have energy of 0. Now, when only one of the particles is excited, we have an energy of epsilon. When only two are excited, we have 2 epsilon. But we can have many different similar to epsilons, right? So the contribution to this guy coming from all different configurations. Okay? We can have particle number 1 and particle number 2 that are excited, or we can have particle number 3, a particle number 74 that are excited. So, okay, so we need to somehow choose for all the different configurations, all the different conditions to fill up all the energies. And we have many of them. As we go up and up and up until n epsilon, there are many different configurations for each energy over here. Okay? And it's actually difficult when you think about it. Now, exactly at this point, we're using represent the energy in an additive fashion. Yes?
You can use the choose function.
I don't want to use the choose function. I want to be smarter than
So you
what I...
can approximate it to a normal distribution.
No. So you're trying to pull me towards the solution of microcanonical ensemble. Compute everything explicitly using difficult combinatorial expressions. Okay, but I don't want to do that. This is, I want to use those two principles, okay, and be much smarter than any mathematician can. Okay? I'm going to use this guy and that guy, okay, in order to compute. I'm not going to use any approximations, normal Gaussian approximation, Levy approximations. Forget about approximation. I'm going to compute it exactly and extremely fast.
So you can use the linearity of the...
So what is EI? Any energy I. I can say the following thing. This is energy of particle number 1 plus energy of particle number 2 plus energy of particle number 3 plus energy of particle of number n. Right? So the total energy is always a sum of the energies of all the different particles that I have inside. Okay? Now, when I'm thinking about states and different representations, I'm going to use the following. I know what are the states of single particles. They are simple. Each particle have only two states, 0 or epsilon. And I want to use this property. Okay? So, when I'm writing z equals to sum of I e to the power minus beta I, I'm basically saying this is sum over all states of e to the power minus beta, and here I have E1 plus E2 plus E3 plus En. I have all of those over here. This is great. Why it's great? Because they all sit in the exponent, and there is a nice property of the exponent. Exponent as a sum is a multiplication over exponents.
And transform the sigma to pi.
So, what?
You can transform the sigma to a pi.
Sigma to a pi. Yes. So the function of all states of e to the power minus beta E1 multiplied by e to the minus beta E2 multiplied by e minus beta E3 e to the power minus beta En. Alright. I have to sum over all the different states of the system. Okay? And I try to convince you that the way to go is to describe all the different energetic states of the system and sum over all different configurations that represent each state. Okay? But this is not the only option. What I'm trying to do now is to say, but let's use the representations of single particles. When I'm counting of all the states, I'm saying, well, let's count first on all the different states of the first particle. You can say, how can you do it? Why can you do it? And this is the second condition. Deal with uncorrelated degrees of freedom. Each particle is unrelated, it's careless about what happens to the other particles. If the first particle is at state 0, it doesn't care if the second particle is at state 0 or epsilon, or the third or the fourth. So the different states of each particle are uncorrelated to the states of other particles. This is why I can say the following thing. Let's first count on the states of the first particle, and later describe all the different states of all the other particles. Okay, so this E1, what it can be, first of all, it can be 0, right? So E1, it's either 0 or epsilon. So if it's 0, it is e to the power minus beta multiplied by epsilon And here I have all states. This is some strike over here that I don't count the states of the first particle. E minus beta E2 multiply E minus beta E3 E minus beta En plus e to the power, because E1 can be, this is the first state that we counted, but we summing up over different states. We have to sum up also over the state when E1 equals epsilon. Minus beta epsilon. And here we have a sum over all states with some asterisks. E to the power minus beta E2, e to the power beta E3, e to the power minus beta En. Okay, this guy equals to that guy. Okay. They're exactly the same. So what we have, we have 1 plus e to the power minus beta epsilon multiplied by all states e to the minus beta E2 multiplied by e to the power minus beta E3, etc., 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 up to e to the minus beta E4. En, thank you. Now I can continue this. I can do this also for the second particle, right? And the third particle, and the fourth particle. And each time I do this for one additional single particle, I'm getting a multiplication of this term, 1 plus e to the power minus beta epsilon. So what I'm getting in total, this is coming from here. It's 1 plus e to the power minus beta epsilon to the power of n. And that's it. Okay? So we got that z equals to 1 plus e to the power minus beta to the power n. We haven't cared about how many representations there are in very specific energetic state of the whole system. We completely forgot about it. Why? Because we could describe the energy as the sum of different particles, and because those different particles are uncorrelated to each other. Okay? So next step is F equals minus B1 over beta log of Z. So F equals to minus 1 over beta log of 1 plus e to the power minus beta epsilon to the power of n. And we are getting that F equals minus n, 1 over beta, it's K Boltzmann T, log of 1 plus e to the power minus beta epsilon. This is the free energy, this is the equation of state. We can compute from here the average energy, we compute everything, whatever you like. I was completely careless about the combinatorial problem. I don't care about this at all. Now, this trick that I have performed over here, it's the only trick that we know in statistical physics how to compute partition function. We don't know anything else, really. All that we are capable of doing, so but you can say about Stas, but you can maybe solve systems where the particles are correlated. So all what we're doing, and people have got Nobel Prizes for that, all what we're doing in statistical physics or in hard condensed matter physics is use a system of highly correlated particles, because most of the systems, the particles are highly correlated. We find a way to represent them such that they look as uncorrelated. Okay? This is very important. We don't know how to sum up, how to compute the partition function when the particles are correlated, only in the very specific cases. We know everything about computing partition functions when the particles are uncorrelated, and when we know how to represent the energy as a sum of different particles. So whatever we're going to solve from here on is, if we have a system and everything looks correlated, right, the physics is going to be how to represent everything such as it appears to us uncorrelated particles. So remember, this is the physics oldest trick, right? You have learned it or you have been taught this in analytical mechanics. Okay, so what is eventually the goal of analytical mechanics? To write Hamiltonian and to write Lagrangian. And afterwards, there was Hamilton-Jacobi, right? What was the purpose of this Hamilton-Jacobi? Yeah, a tough topic.
Found the Hamiltonian such it will equal to 0.
Oh, so you wanted to find an Hamiltonian or represent any question, any problem as an Hamiltonian of a free particle or independent particles that are connected to strings. So this is what we are trying to do also in statistical physics or hard condensed matter physics. We want to describe everything as if, but sometimes we start with particles and the particles are correlated and we do something, we do a lot of magical tricks and eventually we have monsters, but those monsters are completely uncorrelated, but we can do this. Okay? So usually we start with particles, but eventually we describe the system with waves, but the waves are uncorrelated. Great, we don't care that there are waves. As long as they're uncorrelated and we can perform this, exactly this trick. This is what we're going to do. And we can write the energy as a sum, and then we can do this, whatever is described over here. We're always going to manage to compute the free energy, and the moment that we have free energy, we're practically done. Yes?
Why there is always an uncorrelated...
There is not always, but we always want to describe...
How can you always assume that there is...
No, I cannot always assume. This is the only way... Shh. The only way how I know how to solve complicated problems with correlated random variables, with correlated particles, where the particles are affecting each other, is just by describing them as particles that are uncorrelated. And I hope that there is always a way to describe it. So there is a lot of theoretical proofs based on some few theories that very general classes of particles can always be described in some way. But everything that we managed to solve so far, this was the method. Nothing else.
I have a question.
Yeah.
The free energy is always positive, no? Because energy is positive.
Okay.
How did you get...
Why do you think that it's always going to be positive?
Because free energy...
It's U minus Ts. Right? Can be negative. It's not even that. It's not the kinetic energy.
But because the energy is all positive.
By the end, so this is minimal. This is maximal. Total. This is negative. It's fine.
Fine.
There is nothing bad about negative free energies.
Okay.
All right.
You're not judging.
You're not judging the free energies. It can be negative. Okay, so this trick that I described to you over here, and this is where we're going to finish. This trick is called factorization. So all we want to do is to describe the system such that the factorization could be possible. What is this factorization? Factorization is the following procedure. When we have a specific state EI, and we describe the specific state EI as a sum over all energies of all the constituents, of all the degrees of freedom that we have. We will usually call those degrees of freedom particles, but we will see sometimes they are waves, sometimes they are position of many particles. It's degrees of freedom in general. But let's use the name particle. So when any energetic state, we describe by using this first commandment as a sum over the energies of all the constituents that we have inside the system. Sometimes this goes up to infinity because the number of particles that we have inside our system or the quantities that we have inside our system can be infinite. Okay? So for example, we were going to use a representation based on something which is phonons, which are waves inside the particles. The number of waves, or structures of waves that any system can have, can be infinite, and then the sum is infinite. But it doesn't really matter. Let's assume that we have a finite number of particles. Okay? This is the first step. The second step is the states of all different particles are uncorrelated. Now, what we have shown that Z, which is a sum over all states, is what? Is e to the power minus beta, ei, which is the sum over all states, e to the power minus beta, ej, sum over j, all states. This is a presentation that we have used. Now the next step that I have shown to you, that we can do the following thing, is that we can do as Z1 multiplied by Z2 multiplied by Z3 multiplied by Z4 multiplied by Zn. Where what is Zi? So Z1, it is all states of particle 1, e to the power minus beta E1. And Z2 is sum over all states of particle 2, e to the power minus beta E2. And Zi, a sum over all states of particle I, e to the power minus beta ei. This procedure, the description of the partition function by terms of multiplication of different z's, it's called factorization. We cannot assume factorization. We should prove why factorization is possible, and for this we need to represent the energy in such a form and prove the claim that all the different e's are unrelated to each other. Yes?
I remember from thermodynamics that we sometimes divided it from n atzeret.
No, we forget divide by n factorial. I will get to this. I will get to Gibbs paradox later. All right.
Couple that one step later, you perform the discrete Fourier transform and you get some.
I will do this. This is called the Debye model, and we will show how those Fourier transform is actually phonons. Yes. Okay. So, but if you think about it, we have factorization also in some other procedures, right? If we, again, back to probability, where do we have factorization in probability? So, independent random variables, right? So if we have x and y are random variables, and I want to compute the probability density function, the probability anything that is related to those two random variables, if they are independent, and independency also means that they are uncorrelated, this is related to the probability of x multiplied by the probability of y. Sure. Okay, so the factorization that we have over here is the same phenomenon. Because think of what we say. We said, I take one particle, and the different states of this particle are unrelated to the different states of the other particle. So it can be in whatever state it likes. The other particle can also be in whatever state it likes. Now, the states define probabilities. So if the occupation of different energies are uncorrelated, so the same goes for the probabilities. Okay? Now, for example, if I want to compute f of j, the probability jk of particle j to be in state k. Okay. What happens over here? So what actually happens over here, how I compute this, so f of j and k, it is what? So in the denominator, we have the partition function z, okay, of the whole system. In the numerator, we have what? E, the sum over all states, and I will describe in a second what states we count, e to the power minus beta ei. Now, those are not exactly all states, but those are all states when the energy of particle j is ek. So let's see what happens over here. I know how to compute a probability to be in a specific energetic state. Now I'm asking a little bit more refined question based on the factorization. Maybe all the different particles are now independent, so that their probabilities are going to be also independent, and we can somehow not compute the probability of a state, macroscopical state, but maybe we can compute a microscopical probability of a single particle. Right? How we do this? So this is a general description. This is a specific state, so we know we have to compute. This is a specific probability when particle number j have a very specific energy k. This is a general description. We have to divide by z, and we have to take into account all the states with weights e to the power minus beta I that contribute to the specific energy of particle number j at energy number k. So we can write this as we have z over here. Here we are going to have e to the power what? E to the power minus beta, e, we call it jk, minus beta multiplied by all states, e to the power minus beta ei. Why I can write it like this? Because this equals to e to the power minus beta. The total energy is ejk, right? This is the energy of my single particle, plus all the other energies. I have sum over all states, and I divide it by z. So I actually start from here. What is the energy of the system? I'm looking only on the states when this particle jk have a very specific energy. So the energy is something plus whatever I put over here.
What have you done here? What?
Very. I have done something tremendous.
That.
It's late. 2 minutes. Let me finish this argument. What I'm trying to say is the following. Let's try and compute the probability of particle number j, to be in state k. So it has a specific energy. How I compute it? Right? I have to compute all the states where the energy of the particle is this jk, and divided by the total partition function. This is how I compute probabilities, right? So the probability of any state is 1 over z, e to the power minus beta e, and I sum over all the e's that are contributing to my state. This is always the function that I start with. Now, the next step that I do is, well, the energies that I care about are only the energies where this specific particle have very specific energy, one single energy, and everybody else have something else. I don't care what everybody else have. Okay? So this is constrained, this is not constrained. Okay? The next step is just to take this e to the power minus beta ejk and get it out of all the different states. I do not count of all the different states of the other particles. I only care about one single particle over here.
You do what we done in previous.
Yep. I'm doing factorization. Now, let's see. So this is z, and this is z, and I'm using the factorization trick. So this is z1 multiplied by z2 multiplied by z3, and somewhere I'm going to have zj, and I'm going to have zn. Okay. Up over here, I'm going to have e to the power minus beta ejk. All those states, they include particle number 1, particle number 2, particle number 3, all the states except j. So I'm going to have here z1 multiplied by z2 multiplied by z3 up to zn. No zj. Okay. The moment I have written it like this, I can cancel out all the different terms, and eventually I'm left with the probability of a particle to be in a specific state k is e to the power minus beta e jk divided by zj. So you can say, Stas, this is very similar to what we have derived before, but I will say that it's very different. Before, we have probabilities for the whole system. Right? The probability of the whole system is e to the power minus beta, the energy of the whole system, divided by the partition function of the whole system. But here it's different. It's the e to the power minus beta, the energy of one single particle, divided by the partition function of one single particle. I'm not assuming here any macroscopic co-descriptions. I don't have a heat reservoir. I don't have anything. Okay? I started with probabilities that describe the whole system. I assumed that they are somehow uncorrelated, all the different particles, and I obtained that the same form that describes the whole system also describes one single particle. So it's too late, and I think I'm going to repeat the last part on Tuesday because it's actually important. And I'll see you on Tuesday. That's it.
שאלה.
כן.
אני גם שאלתי אותך בהרצאה
כן.
היו על זה, אם אני רוצה להרחיב מספיק